Section 4.4 is the properties of rational functions. A rational function is a function that is a quotient of two polynomials, like x over x plus 2. Its domain is anything that does not make the denominator equal to 0. So one rational function is 1 over x squared. We're going to try and graph that using a table. So here I've made a table with some x coordinates. Go ahead and pause the video and find their corresponding y coordinates. So we found the y coordinates. If you plug in -2, you get 1 over -2 quantity squared, which ends up being positive 1/4. Then -1, 1, -1/2, 4. 0, we would end up with a 0 in the denominator, so that's not possible. We'll talk about that in a second. 1/2 would give you 4 again, 1, 1, 2, and 1/4. So we plotted these points. When we plug in 0, that's not possible, so that's actually going to give us a vertical asymptote. We're going to talk a little bit more about that in a minute, but we're actually going to have a vertical asymptote right here on the y-axis, just like we do with 1 over x. We also have a horizontal asymptote on this graph. What kind of y-coordinate will you never get out of 1 over x squared? Well, if you have a 1 in the numerator, you'll never get a 0, because the only way you can get 0 is 0 divided by something. And also you'll never get a negative number because of that x squared. So we're going to have a horizontal asymptote at x equals 0 also. We'll get a little more into that in the next couple slides. So if you connect the dots, this is what it ends up looking like. It's very similar to 1 over x. Instead of being in the first and third quadrants though, it's just in the first and second. All your y coordinates are positive. So this is a new parent function that you should be able to do transformations from. From here on, there's some notes. I would pause the video and write down these notes real quick. So the first thing is a vertical asymptote. A vertical asymptote is a line that as x approaches that coordinate, your y coordinate is going to either positive or negative infinity. In this case, they both go up towards positive infinity. The easy way to find your asymptotes is the x values that make the denominator 0 that don't also make the numerator 0. So on this example, 0 makes the denominator 0, but it doesn't also make the numerator 0. And then we'll get into horizontal asymptotes in a little bit. So now we want to graph this function y equals 1 over x minus 2 quantity squared plus 1 using transformations. Real quick, I want you to pause the video and write down what is the parent function and what transformations has been done to it. So your parent function is 1 over x squared, and you have a plus 1 on the end that moves the whole function up 1, and you have a minus 2 attached to your x, which moves the whole function right 2. So now you could use the transformations that we talked about in chapter 2, especially with these asymptotes. It's really easy to transform this. I'm going to show this using the table method, but it's whatever method works best for you. So I start off with my anchor points. I have my x column and my 1 over x squared column, and my anchor points are -1, 0, 1, and then my horizontal asymptote. So 1, vertical asymptote, 1, and 0. I'm going to start with anything that's attached to y. There's nothing multiplied, so just what's added or subtracted. So I have this plus 1 on the end, which means I'm going to add 1 to all of my y coordinates. So 1 plus 1 is 2. My vertical asymptote does not change because if you move an infinitely long line up 1, it's still an infinitely long line. 1 plus 1 is 2. 0 plus 1 is 1. Now that's everything that's attached to y, so now I'm going to do everything that's attached to x. I have this x minus 2. Remember, whatever we do to x, we always do the opposite. There's nothing multiplied, so we're just starting with add or subtract. We have this x minus 2, which really means we're going to add 2 to everything because we're going to the right. So -1 plus 2 is 1, 0 plus 2 is 2, 1 plus 2 is 3, and then our horizontal asymptote doesn't change. So now the point that was originally at -1, 1 is at 1, 2. The vertical asymptote that was originally at x equals 0 is now at x equals 2. The point that was originally at 1, 1 is now at 3, 2, and the horizontal asymptote that was originally at y equals 0 is now at y equals 1. So go ahead and pause the video and plot this to graph. So we graphed our parent function on the previous slide. Now you can see this transformation. This horizontal asymptote was moved up 1, this vertical asymptote was moved right 2, and then everything else was done the same. Vertical asymptotes. So we said that vertical asymptotes are anything that makes the denominator 0 that don't also make the numerator 0. So first step is always to factor completely. Factor the numerator and factor the denominator. Find anything that makes the denominator 0, basically any factor that is in the denominator that is not also in the numerator. So lowercase f of x, x over x squared minus 4, the numerator is completely factored, but the denominator is not. So go ahead and pause the video and factor that denominator. So x squared minus 4 is a difference of squared, so that means it factors into x plus 2 and x minus 2. So this one you have two factors in the denominator, and neither of them show up in the numerator. So that means that both of these, whatever makes these 0, are vertical asymptotes. So in this case we have two vertical asymptotes. We have a vertical asymptote at x equals negative 2 because that makes x plus 2 equal to 0. And we have a vertical asymptote at x equals positive 2 because that makes x minus 2 equal to 0. So now go ahead and pause the video and try the next three. Remember, factor completely and then whatever makes the denominator 0 that doesn't also make the numerator 0. So lowercase g of x is already factored completely. X minus 1 is in the denominator, but it is not in the numerator, so that means it's going to be a vertical asymptote. So your vertical asymptote is x equals 1. Capital F of x is also factored completely. You can't factor x squared plus 1. So x squared plus 1 equals 0, x squared equals negative 1. That is not possible, so this one does not have any vertical asymptotes. This last one, I factored the numerator and the denominator, so you get x plus 3, x minus 3 in the numerator, and x plus 7, x minus 3 in the denominator. X minus 3 shows up in both the numerator and the denominator, so it is not a vertical asymptote. The only vertical asymptote is x equals negative 7. So this is still a domain issue. It's still making the denominator 0. If it's not a vertical asymptote, what is it? Well, it's a hole. So if you haven't already done so, go ahead and pause the video and write down these notes on holes down here. So what a hole is a point that makes both the denominator and the numerator equal to 0, and you can tell it cancels, a factor cancels here. That's when you know there is a hole. So at x equals 3, there's actually a hole that is an open circle in the graph, but we need to find its y-coordinate. So the way that we do that is we plug this 3 back into the function. After we cancel off this x minus 3 factor, you plug 3 back in for x. So just like a normal point, holes are written as coordinate points. X is equal to 3, that's what made both of these equal to 0. I canceled these off and plugged the 3 back in, just like you would a normal y coordinate, and you end up with 3/5. So the y coordinate is 3/5. Very, very rarely will be the y coordinate 0. So if you get y equals 0, you probably did something wrong. 0 divided by 0 is not, in fact, 0. Make sure you cancel this factor first before you plug that 3 in. Anything that makes the denominator 0 is either a vertical asymptote or a hole. It cannot be both. It's always one or the other. In behavior or horizontal asymptotes, what happens when x get really, really big in either the positive or the negative direction? Go ahead and pause the video and write down these notes. Case number 1 is when the degree of the numerator is smaller than the degree of the denominator. Doesn't matter how much smaller, but it's smaller. So that means your horizontal asymptote is y equals 0. That's like our 1 over x and 1 over x squared. Case number 2 is when the degree of the numerator is equal to the degree of the denominator. So like x squared over x squared plus 4. Then your horizontal asymptote is going to be the quotient of the leading coefficients. So you divide the leading coefficients and you end up with y equals some number that is not 0. The last one is called an oblique asymptote. It's when the degree of the numerator is 1 more than the degree of the denominator. We'll never do anything other than 1 more. In that case, your horizontal asymptote isn't actually a horizontal asymptote, it's a slant line. It's an oblique asymptote. You need to do polynomial division, and the quotient that you end up with is your oblique asymptote. Now we want to find horizontal and oblique asymptotes. So using the notes on the previous slide, I want you to pause the video and find the horizontal asymptotes of capital G of x and capital R of x. So the first one, I notice that I have the same degree in the numerator and the denominator, so it's a case number 2. So to find the horizontal asymptote, I divide the leading coefficients. So y is equal to 8 divided by 4 or 2. So you have a horizontal asymptote at y equals 2. Capital R of x, I notice that my degree of the numerator is smaller than the degree of the denominator. So that means it's case number 1, y equals 0, you're done, nothing else you have to do. This last one, capital H of x, what I notice is that the degree of the numerator is 1 bigger than the degree of the denominator. That means I'm not going to have an horizontal asymptote. I'm actually going to have an oblique asymptote. So to do that, I need to do polynomial division. Set up the division it tells me to do, numerator divided by denominator, that's what fractions are, with some placeholders in here for all my missing terms. So now go ahead and pause the video and actually do this polynomial division. So I did the polynomial division as far down as I can. I cannot multiply x cubed by anything to get 2x squared. So this is my remainder down here. We don't actually care about the remainder. All we care about is this part right here. So our oblique asymptote is y equals 3x plus 3. So whenever you have a case 3 problem where the degree of the numerator is 1 more than the degree of the denominator, you do polynomial division. Whatever you end up with here is y equals, that's your oblique asymptote. So whatever makes the denominator 0 is either a vertical asymptote or a whole. And then oblique asymptotes and horizontal asymptotes, you have 3 cases. You can only have one per problem. So you won't have multiple horizontal asymptotes, but you could have multiple wholes or vertical asymptotes.